Alright guys, welcome to IC. We're going to be looking at this homework assignment right here. Got single replacement reactions up at the top, and you've got some double replacement reactions on the bottom. In order to make this process a little easier on you, you're going to want to have your solubility rules in front of you. Alright, let's go ahead and get started. In class, I already did questions 2 and 3 up at the top. So we're going to roll straight into question number 4 on the single replacement reaction worksheet. Now, just as a refresher, you need to be careful about thinking about what makes single replacement reactions actually work. So you're always looking to see whether the alone one, the one that's alone, is higher in reactivity. So for us, in question number 4, you have a unique situation. You have a nonmetal trying to cut in. And in your notes, I already explained what makes these work, but let's go ahead and refresh your memory. In order for a single replacement reaction to work, you always check metal reactivity or electronegativity values. So over here, I think we already mentioned that fluorine is the most reactive of all of the nonmetals. In this particular sample problem, we have iodine trying to boot out bromine. So we are hoping that iodine is more reactive than bromine. So here's iodine. He's right there. He's the one that's trying to cut in. He is trying to cut in on bromine, and bromine is higher up, closer to fluorine. So in this particular reaction, iodine is not the more reactive nonmetal. So for question number 4, this is pretty easy. This is a no reaction, NR. So let's skip that one and go on. Number 5. So aluminum bromide and chlorine. All right, let's check this one out. So the one that is alone is the chlorine. We are trying to see if chlorine is higher in reactivity than bromine. So go check out your periodic table again. All right, so which one needs to be higher again? The one that is alone. Chlorine is alone. Is chlorine more reactive than bromine? Yes. All right, so this reaction does work. You do need to start predicting products. Again, this is question number 5. All right, so let's get this one started. First step, predict your products. So aluminum, the metal, is not the one getting the boot. The one getting the boot this time are the nonmetals. So these are the guys that are going to be switching. So who's aluminum's partner now? And chlorine turns into chloride. Good job, because he's part of a compound now. And who got the boot? Bromine, yeah, because bromide will turn into bromine. Good job. All right, now that we got the words done, let's proceed on to the formulas. So aluminum, element number 13, got to check his charge. He's a positive 3. And how would I know that? Well, he wants to be like neon, atomic number 10, and his number is 13. So that gives him a positive 3 charge. Bromide, he's a halogen right next to the noble gases. What's his charge? He's negative 1. So we're going to have to do a little bit of balancing here. Like that. Okay, now we're going to add chlorine. And the thing that you need to remember is that chlorine is a nonmetal, but he is not a noble gas. He's not on the very last row of metals. So anytime you have a nonmetal that is not a noble gas, you got to double them up. Okay, so that's chlorine gas. Okay, product side, aluminum is now going to be combining with chlorine, and chlorine's a halogen. This guy's still positive 3. What's the charge of chlorine? He's right next to the noble gases, so he's actually a negative 1. So to balance the formula, you're going to have to be a little careful there and put a 3 on the chlorine. Bromine. Bromine is a nonmetal. Is he a noble gas? No. So what are you going to do? Double them up. All right, so this is the bare bones skeleton. At this point, what you need to do 2 things. You need to balance the reaction, and then you need to dress the reaction up with solubility. You need to check those solubility rules. So in the front, that's where we place all of the coefficients. Let's see if we can eyeball. 1 chlorine, 1 chlorine. Oh, I'm sorry, 1 aluminum, 1 aluminum. 3 bromines, 2 bromines. Oh, that's interesting. What do you think the best strategy would be if you have a 3-2 combination? Yeah, let's go for 6. Alright, over here you have 3. To make that a 6, you're going to put a 2. Over here we have 3. To make that a 6, we're also going to put... Oh, I'm sorry. Over here you have 2. To make that 6, you're going to put a 3. Alright, now unfortunately you did change your aluminum over here. You see how now you have 2? Kind of need to fix that over here. Alright, you also messed up your chlorine right there. You have 6 chlorines on your product side. To make this a 6, what are you going to do? Yeah, stick a 3. Alright, it's balanced. What do you do now? Label solubility. So you're going to have to grab your solubility rules. Alright, here we go. So let's start with that aluminum bromide. So the rules for bromides are they are soluble except silver, mercury, and lead. Well, luckily we don't have silver, mercury, or lead. That means that this guy is soluble. What is the symbol for soluble? AQ. Good job. Now chlorine, see the Cl2? This is not a solid, guys. What is this one? This is a gas. Good job. You only check solubility on like ionic compounds. Okay, let's keep going. Aluminum chloride, I'm going to read the rules for chlorides. All chlorides are soluble except silver, mercury, and lead. Well, we don't have silver, mercury, or lead, so we're going to label that AQ. And then over here, this is another non-metal, and he is a gas, so just put a G. Alright, that was question number 5 on single replacements. So just to make this kind of a well-rounded vodcast, I think what I'm going to do is I'm going to do one more problem up at the top that I think is kind of unique. I'm going to do number 7. Okay. For number 7, this is a single replacement reaction. The guy that's trying to cut in is calcium. And you're like, what is calcium trying to cut in on? Well, you have to remember that this is an acid. Why don't we go ahead and get the formula here. You have a hydro and an ick. If you remember your rules for acids, anytime you have a hydro ick, this comes from an ide ion. So who is chloride? Chlorine. And what's his charge? He is a -1. So to make him an acid, what do you stick in the front? Yeah, hydrogen. And you only need 1 hydrogen. Each hydrogen is a +1. So that is hydrochloric acid. Now if you got calcium sitting over here and he's trying to cut in, who do you think calcium is trying to push out? The chlorine or the hydrogen? Which one acts like an alkali metal? Yeah, that's right. The thing that you have to remember is that the periodic table, hold on the periodic table, you need to treat hydrogen like an alkali metal. It's sitting on the top of all these alkali metals. So hydrogen is going to be treated like a metal. And in this single replacement reaction, calcium is a metal and he's the guy that's trying to cut in. Calcium is trying to push hydrogen out. So what you guys need to do is go to your metal reactivity series. Now this one's unique. Go to your metal reactivity series and I'll show you what I mean. On the metal reactivity series, if you find calcium, he's located here on the top half of your metal reactivity series. Read the box. Read the box right here. These metals displace hydrogen from water. They react readily to form compounds. Underneath that box it says these metals displace hydrogen from acids. Now guys, here's how it goes. If the reactivity is increasing as you go up. If these metals right here can react with an acid, what do you think the guys at the top can do? They can also react with an acid. Alright, I hope that makes sense. So up at the top, you may want to add this like on your notes. The guys at the very, very top can react with water and acid. So, bottom line, this reaction works. And calcium will kick out hydrogen. You need to predict your products. So if calcium can cut that hydrogen out, What do you think the hydrogen is going to turn into? Hydrogen gas. Good job. If hydrogen's by himself, he is going to be doubled up. He's going to be a gas. The compound that is going to be formed is calcium and chlorine. Now you're making a compound, you got to check their charges. Calcium is positive 2, chlorine is negative 1, so to make this nice and balanced, you have to double up the chlorine. What we skipped, because I thought it would be easier, is we skipped the words. So can you guys go back and do your words? The products is going to be hydrogen gas. You can just say hydrogen if you want, but I'm going to be proper. I'm going to say gas and calcium chloride. Alright, so I just kind of skipped the words because it was hard to explain unless you could see it this time. Alright, so there's our products. Up at the top right here, this is the skeleton form right here, you see? I've got all my formulas balanced, but what are the 2 things you expect me to do right now? What 2 things do you think I'm about to do? Once you get your skeleton, you have to do 2 things. Yeah, you got to balance the reaction and then label your solubility. Okay, so I'm going to balance with coefficients placed in the front. Oops, sorry, that was a little bit long. There we go. Okay. All right. On the left, 1 calcium. On the right, 1 calcium. On the left, 1 hydrogen. On the right, 2 hydrogen. Come back. Let's get 2 hydrogen, shall we? We also have 2 chlorines, but if you look over here, you already got 2 chlorines. It's all beautiful and balanced. Label solubility. Starting on the left, calcium is just sitting here by himself. He is a metal, correct? What state of matter? Solid. All right, everyone always gets confused about acids. Remember, the hydrogen in the front is behaving like an alkali metal. Remember that? If you check your solubility rules, most of the solubility rules will say something along the lines that, you know, everything's soluble or everything is insoluble except when you have alkali metals. The general rule is anytime you have alkali metals, they're always soluble, and hydrogen can be treated like an alkali metal. So all your acids will forever and ever be soluble, AQ. How do you think we should label H2? He's not a metal. Yeah, he's a gas. Good job. Now let's check the solubility rules for the chloride ions. All chlorides are soluble except silver, mercury, and lead. Well, we don't have silver, mercury, or lead, so how do you want to label that? Aqueous. Good job. Done. All right, now that we've done a few problems on the top, I'm going to switch gears, and let's do some problems on the bottom. Now, I've already done question number 2 in class, so I was thinking to start with question number 3. All right. For double replacements to work, in the products, we are looking for the formation of water, a gas, or precipitate. Now, the only way for me to figure this out is I just jump straight to predicting what the products are. So, copper 2 bromide. Copper is going to switch partners. Who's copper going to like to be with now? Yeah, chloride. Good job. The other product is going to be aluminum who? Yeah, aluminum and bromide. Alright, so I predicted my products in word form. And now what I'm going to do is I'm going to go to my solubility rules. And let's just check the products. We're looking for precipitate. Copper 2 chloride. Rule for chlorides. All chlorides are soluble except silver, mercury, and lead. Huh. You do not have silver, mercury, or lead. So far, this dude right here is soluble. This guy's aqueous. So we're still trying to seek out the precipitate. Let's keep going, alright? Let's go for bromide. All bromides are soluble except silver, mercury, and lead. Oh. Dang it. We don't have silver, mercury, or lead, guys. Guess what? This guy is also soluble. You can't have 2 solubles, guys. Do you know what that means? No reaction. Alright, so I'm repeating one more time to make sure you heard me. That is a no reaction. That was question number 3 on the bottom. Just saved you a ton of time. All right, question number 4. All right, question number 4. Again, I'm going to do the same process, okay? Got to predict my products. After I get my products figured out, we'll check to see if we have a precipitate or something. Calcium. Who's calcium's new buddy? Carbonate. Good job. Okay, remember, you don't want to stick 2 metals together. You wouldn't say calcium sodium. That would be terrible. We're not doing metallurgy. All right, who's sodium's new buddy? Sodium acetate. Good job. All right, we got our words. Let's check our solubility, shall we? Carbonate. Let's find those guys. They're on the bottom. All carbonates, sulfites, phosphates, and chromates are insoluble, except those of alkali metals and ammonium. You need to check, is calcium an alkali metal? He's right here. Is he an alkali metal? No! Nice! So, hey, I think we found our precipitate. It says that all carbonates are insoluble except for alkali metals and ammonium. Sweet! Alright, so this right here is going to be labeled as insoluble. What symbol represents insoluble? What symbol? AQ or S? Good job, that's S. Okay. Sodium acetate. Well, sodium, FYI, is an alkali metal. I don't think we need to look any further than that. How do I label him? AQ. Yep, he's able to dissolve in water, so he's aqueous. Yay, we have a precipitate. That means that the reaction works. Let's go for it. Let's start doing some formulas. All right, calcium. Ca. He is a +2. Acetate. Ends in an 8. Check your list. He's a big fat ion, man. He's huge. But he's -1, so how do I balance that out? Acetate is a huge polyatomic ion, and if you need more than one, gotta use some parentheses. Alright, sodium, Na, carbonate, CO3. Check charges. +1 and -2. Yeah, so we've got to fix that up. Na2CO3. Keep going. You already got the charge of calcium. You already got the charge of carbonate. And this guy is our solid. He's our precipitate. So I'm going to go ahead and label that right now. And then sodium acetate. Na is a +1. Acetate. Let's see. C2H3O2. -1. And I already know he's soluble, so I'm going to go ahead and label AQ. Okay. There's our skeleton. We have some of our solubility rules right here. So you got like some right here, and you got some right here. But we need to finish it. How do you finish this problem? What 2 things do we have to do at this point? Balance the reaction and finish labeling that solubility, okay? Let's do it. Oops, sorry. Coefficients in the front. Let's see if you guys can eyeball, okay? Calcium 1. Calcium 1. This big old polyatomic ion called acetate. Looks like you've got 2 of them. How many over here? Oh, careful. That's a big old chunk. Do you see any parentheses around this guy? No, there's only 1. So how can I show 2? 2 right there. Alright, that gave us 2 sodiums, and look, we already have 2 sodiums. The only thing left to do at this point is to finish your solubility, because I kind of started, but I didn't finish. Alright, acetate, this calcium acetate, let's check that. Alright, acetates are on the top. It says all nitrates, chlorates, and acetates are soluble, and there doesn't seem to be any exceptions, so let's label that as AQ. Over here, sodium carbonate. Sodium is an alkali metal. So that's easy. All alkali metals are soluble. Alright, this is now officially finished. Once you get those solubility rules, they're done. Is this starting to make sense? Think we have enough time for one more if we go quick? Alright, let's see. To balance this out, I would actually like to do number 8. Number 8's kind of unique. All right. To start this one, I'm actually going to show you the formulas, okay? Copper 2. What's the charge of the copper here? Positive 2. Hydroxide. OH. He's polyatomic and on your list. He is negative 1. Alright, so balance those charges out. Cool, cool. Acetic acid. There's no hydro in the front of this acid. It's just an ic acid. So if you have an ic acid, what kind of ion do you need to use? 8. That's right. So we are looking for acetate. What is the acetate ion? Yeah, it's that really big one. This one is C2H3O2. There's the ion, and he has a negative 1 charge. So to make him an acid, what do you have to stick in the front? 1H. Remember, hydrogen's always just positive 1. Alright, the reason why I wanted to show this one is because it really is unique. It is a double replacement reaction, but what you have over on the left is you have a hydroxide, which is going to act like a base. Over here you have acetic acid with the hydrogen in the front. That's an acid. Anytime you have a base and an acid, technically, this is a neutralization reaction. Neutralization reactions are double replacements. They're just kind of hard to see. So, who is going to be copper's new buddy? Yeah, it's this guy. Okay, the cation and the anion flip. So, hold on. Cu, C2H3O2. I'll remind you the charge is this guy's plus 2, this guy's minus 1. So, to balance, we'll have to go like this. All right, get a couple of the acetates on that copper. Alright, now the next piece, let's see if you can see it. You have hydroxide ions on the back, and then you have a hydrogen ion in the front. What is the combination of these two ions? What do they make? They make water! Yay, you remember. I need you to remember that I told you that hydrogen and hydroxide will combine to make water. And I know it seems confusing because on the left you have 2 hydroxides, huh? Yeah, but you need to remember that we made copper hydroxide with 2 hydroxides to balance the charge of the plus 2 on that copper, so that's why you see 2 hydroxides. But when you make the product, you're rebalancing all over again. Does that kind of make sense? Alright, there is your skeleton, and I think from here you could probably balance and label your solubility. Oh, by the way, on water, you need to label water as an L. Liquid is a pure substance. So over here on the end, sorry. Over here on the end, just label your water as a liquid. Acetates are always soluble, so I'm going to go back over here. And then, I don't know, is copper hydroxide soluble? Let me check that real quick. All hydroxides are insoluble except calcium, strontium, barium, and alkali metals. Ooh, fascinating. So you actually have an insoluble reactant right here. That should be labeled as a solid. That isn't going to stop the reaction. What will that do, guys? It'll slow it down, but it's not going to stop or prevent the reaction from working. Especially not with an acid. Acids are pretty corrosive. So, alright everyone, this isn't balanced yet. You do need to balance this with coefficients in the front, but unfortunately, the vodcast, I'm just about done. So, alright, I hope this helped you guys out. Thanks for watching.